This is TMUA 2020, paper number 2. Let's do this thing. Question number 1. Find the complete set of values for this crosses or touches that. So basically, when I solve the two things, they cross or they touch, which means that the discriminant of whatever it is that I'm solving is greater or equal to 0. Equal to 0 if they just touch, greater if they cross in a couple of places. So you just set them equal to each other, you rearrange to make a quadratic, so when you when you add 2 you get 4, when you take away 1x you get take away x, but then you can factorize this. Then you can call this number, which is just a 1a, this number b, and this number c, and you can just say b squared minus 4ac needs to be greater or equal to 0. You put in everything you've got, you make a second quadratic, this time in k, you sort it all out, it ends up being this factorizes to this. And now just remember how to solve quadratics, right? You can draw a graph if you want to, but it's got roots at 5 and minus 3. You're looking for when is this quadratic greater than 0 or equal to, so you need to be greater or equal to 5, less than or equal to minus 3, which is E. Good. Question number 2. So it's tempting to do some very complicated trigonometric identity stuff here, but it's actually much easier than that. Always bear in mind you can just get out your basic triangles, your basic SOHCAHTOA triangles to do this kind of question. So if tan of theta and theta is here, and this is a right angled triangle maybe, if tan of theta is 2, we can just say, well, tan of theta is opposite over adjacent, so we can just call this 2 and this 1, and that makes tan of theta 2. Now, of course, what's this side? We're using Pythagoras, it's just root of 1 squared plus 2 squared, which is root 5, and so cos of theta is going to be adjacent over hypotenuse, which is 1 over root 5, which notice how these don't have root 5s, so I just rationalize it by timesing by root 5 over root 5 to get root 5 over 5. Now, that is one of the answers, I think. Yeah, it's that one, but that's actually not the right answer. And the reason for that, you just need to be a bit careful with this. You know the angle is here. Now, if tan of theta is positive, look at the tan graph right here. If tan is positive between 180 and 360, that means the angle is between 180 and 270, right? That's where tan is positive, where it could be 2, somewhere over here. It's not over here, right? So the angle is between 180 and 270, but then you look at the cos graph and you go, okay, well, between 180 and 270, the cos graph is negative. So actually, we're looking for a negative value here. So the answer is going to be negative this. And I know the triangle kind of breaks down when you do that, but this is a bit like that whole seeing electrons as both a wave and a particle, I guess, if you want to be grandiose about it. You're allowed to see these trig questions as both they're graph questions to get a positive or negative kind of idea, and as these basic triangles to just understand what the numerical value is. You're allowed to do that, so it's fine. Question number 3. Spot the mistake question takes a little while, but what you spot eventually is that they've cancelled this 2 with these 2's to just get this line here, but what they should have done is it's take away all of this, not just take away this, take away that. It's take away this in a bracket, which of course means take away, it means a plus 1 here. That's the mistake, it's on line 2, so the answer is C. Number 4. So this is making a statement about numbers. Every positive integer n that is greater than 6, let's stop right there. If any number in this list is not greater than 6, we can immediately cross it out as a counterexample, because this statement isn't talking about numbers that are less than 6, it's talking about numbers that are greater than 6. So this is irrelevant. This is a bit like when you're sitting in a sixth form assembly and they're like, anyone who hasn't finished their UCAS application, if you finished your UCAS application, you don't bother listening to the rest of that sentence, do you? You just get out your phone, which is presumably already out, and you do whatever you're doing on that. You don't listen to the rest of it. I don't need to consider this because it's not greater than 6. Anyway, any positive integer that's greater than 6 can be written as the sum of 2 non-prime integers greater than 1. So let's just try it with 7 and 9 then. So 7 is 1 plus 6, but of course 1 is not greater than 1, so that doesn't count. It's also 5 plus 2, but 5 is prime, and actually so is 2. I'm looking for 2 non-primes. 3 is prime, so that doesn't work, and that's it. So 7 is a counterexample. I cannot write 7 as the sum of 2 non-prime integers that are both greater than 1. So 7 is a counterexample. 9, the same thing. You run through it, they end up either being 1 or just one of them is prime every time, or both of them. And so both of those are counterexamples. The answer is 2 and 3, G. 5, when you're doing these graphs questions, always think about the intercepts first. So what about the y-intercept of this thing here? Well, the y-intercept happens when x is 0, obviously, so let's put in x is 0. 2 to the power 0 is 1, plus 1 plus 2 to the power 0 is 2, so this is 1 over 2. Now, all of the graphs could do that, so that on the face of it, that doesn't help so much. But it does help when you next consider what happens when x is really, really big. What happens when you just put in a really, really big x value? You get 2 to something really, really big, which is just a really big number, over 1 plus that same really big number. But that's essentially, if the number is really big, just a number divided by itself, because the plus 1 almost doesn't matter anymore. Imagine a billion divided by a billion 1. That's basically just 1. And as the number gets bigger and bigger, it just becomes 1. So this number crosses the y-axis at half and then bounds up to 1. So we're looking at a graph that goes upwards towards an asymptote, and the only graph that does that is A. It crosses at half, goes upwards to an asymptote, whereas all the other ones, like this one, is reasonable, but it goes downwards, and likewise these. So yeah, number A. 6. Whenever you read a thing that says necessary, which of these things is necessary, always look for a counterexample. Now, sometimes that's hard to do, and you might need to get out other tricks, but always look for counterexamples. This is a bit like if you claim that to get an A star in Maths A level, it's necessary to watch R Drew, the YouTube channel R Drew, or R Drew 2. If you can just find someone who's got an A star in A level Maths who hasn't watched that channel, then it's clearly not necessary, right? You just need to find the one counterexample. It only takes one, and then it's not necessary. So can we find counterexamples? Can we find graphs that do this, that got the A star in Maths, but don't do these things? Didn't watch the videos. Oh yeah, because essentially what this is saying is I want a graph that the area between 0 and minus 5 is the same as the area between 0 and 5. Let's just draw this completely random graph and pretend that if this is minus 5 and 5, pretends that this chunky area here is the same as this area plus this area added up, which it looks like it's roughly could be. Well, this graph is not any of these things, it turns out. This suggests that the graph is symmetrical around the y-axis. This clearly isn't. So that's not necessary, because here's the counterexample. This is just a straight line graph. It's just a constant, which would clearly work to make this true, because you just have two rectangles that equal each other. But it's not this. This is a counterexample, so that's not necessary. And this is saying that it's actually, it's you flip it and then flip it again, so it's symmetrical in the y and y equals x. Again, that's probably true, that probably makes this true, but it's not necessary, clearly, because this graph does this and isn't that, obviously. So none of them are necessary. Always look for counterexamples. 7. Again, it's not a necessary question, it's a sufficient question. And counterexamples is also relevant here. You can make basically the same statement, right? If you say, is it sufficient to watch R Drew YouTube channel to get an A star in Maths? Well, if someone watched the videos but got an A, clearly it's not sufficient. Clearly you have to do something else to get one. And again, it only takes one thing that breaks the trend, and then it's not sufficient. So okay, we're looking for parallelograms that have PQRS, that have length of PQ equals length of QR, and we're going to try and do this without it being a square. Well, I can do that by doing this, right? A rhombus. PQ is equal to QR. It's a parallelogram, but it's not a square. So this is not a sufficient condition, because here's something that only got an A, not an A star, so it's clearly not sufficient to use the analogy. So this is no. This, can I find diagonals that intersect at right angles but not be a square? Yeah, well, you can just draw one much longer than the other, clearly intersect at right angles, and it makes a kite. It's also a parallelogram, but it's clearly not a square, so that's not sufficient either. And here, can I make the angle PQR equal to QRS? Well, actually, those are co-interior angles, right, if it's a parallelogram. So they must add up to 180. If they're equal, that means they must be 90. Can I think of a quadrilateral that has two angles 90 and is a parallelogram but not a square? Yeah, I went to year 4 maths, so we learned about rectangles. There it is, so that's not sufficient either. No, no, no is the answer to that question. 8. This question is trippy, man. It's the second worst question on the paper after question 20, which is just awful. You see these questions a lot where they're asking where's the mistake in the work. They're trying to prove this statement. They get this counterexample, 3 plus 4 modded is 7, 3 modded plus 4 modded is 7, but 7 is not less than 7, so it's false. That's a perfect proof. I've never seen that. I've done quite a lot of TMUA papers now, and I've never seen them actually display a proper proof. So that one really messed with me. I was like, what is going on here? You just have to have confidence in yourself. You just have to have the confidence to be like, actually, there's nothing wrong with that. Fine. The person who wrote that question was laughing the entire way through it, I think. Question 9. Trying to evaluate this thing in radians, but the calculator only works in degrees. what kind of calculators you have, mate. Anyway, so we just need to convert the input of the trig function to degrees. We do not need to convert this thing because the radians to degrees thing only matters when you input into a trig function. So the answer is not going to be any of these. It's either going to be C or F, because you don't need to change this x, you just need to change this one. Now, of course, pi radians is 180 degrees, and we want to type in 4 radians, right? Because they want to evaluate this in radians. Calculator only works in degrees. They want to evaluate 4 radians, but they need to find out what that number needs to be in degrees. So we need to find 4 radians. So divide by pi, then times by 4, and that will be how many degrees we have. So we put that many degrees in there, which puts in there. And then we have, this doesn't change, that's still a 4, and then it's 180 times 4 divided by pi. So the answer will be F. 10. So which of these must be true? Now, must be true, that's just a less fancy way of saying necessarily true. And we went over how to do necessarily true questions earlier. We find counterexamples, right? So we try and think of a counterexample, and if we can find one, then it doesn't have to be true. Now, if we can't find one, maybe it is true. Or maybe you need to think more logically about how you could show that it's true. Now, this is very relevant for this first one here, because A less than D, you think, well, okay, I can make this one true with being A bigger than D by just making B quite a lot smaller than C, and that would definitely work, like 10 and 1, and then 100 and 1, and then I'd be fine, like this, I'd break this. But then, of course, when you swap B and C over, everything gets messed up, and it would be fine the other way around. So it becomes very difficult. You actually can't find a counterexample, and that's because this is actually true, and you can prove it, right? You can just take this one and add them together. So just add them down here: 2a plus b plus c, c plus d plus 2d. These obviously will cancel and divide by 2, and we end up with a definitely being less than d. So if you can't find a counterexample, if you've got plenty of time, just assume that you are not missing anything, and it's because it's true. Or if you've got plenty of time, actually logically prove it. B less than C, it is very easy to find a counterexample for. You just make B a bit bigger than C in the first one. But if you make A much less than D, it will still work, and then when you swap them over, it still works, because of course D is much bigger than A, so it just works. So this definitely doesn't have to be true. Here's the counterexample. And the last one is kind of just logically very true. If you look here, A plus B is bigger than 0, so A plus B is bigger than 0, but C plus D is bigger than A plus B, which is bigger than 0, so C plus D is bigger than 0. And when you add two things that are bigger than 0, A plus B and C plus D, you're going to be bigger than 0. So this is just definitely necessarily true. So it's F, 1 and 3. 11, this one was a really fun question, I thought. What you want to do is you could actually, if you had square paper in the exam, you could draw this. Like, you could just keep drawing it until you got to these values. The better logical way of thinking about it is to just name all of these points where the graph turns. So just label them all with their coordinate points here, and then you can say, well, actually, okay, 0, 0, 2, 2, 4, 4. The next one is going to be 6, 6, right? Because it loops down to 6 here, down to 6 there, 6, and then it's going to go to 6, 6. So actually, this top corner is just going to be even integer pairs. 2, 2, 4, 4, 6, 6, 8, 8, and so on, all the way to 100, 100. So let's just pretend we've drawn the whole thing, and we've got to 100, 100 here, which of course makes this just straight down, means the x-coordinate hasn't changed. The y-coordinate goes to minus 100, because it's just going to be 4, 4 to 4 minus 4, 100, 100 to 100 minus 100. Keep going round, that's going to be minus 100, minus 100. This is going to be going, now be careful here. Again, x-coordinate doesn't change, so it's still minus 100, but y-coordinate is 2 less than this one, right? Because it's 2 underneath it, so that's going to be 190, minus 198. And now we can actually just look which of these go through it. 99, 100 is just 1 to the left of this, that's there, so that's definitely on it. 99 minus 100, so that's 99 across, which is here, minus 100 is down here, so that's on it as well. You just keep going through, they're all on it except for that one. Minus 100, 99 is in the middle of these two things here. It's there. So that one's the one that's not on the line. 12, quite a heavy logic question here. You've got A less than B, you've got trapezium rule estimating an integral essentially. So let's just draw this very quickly. Here's a thing, A and B. Now if you're using trapezium rule and you get an overestimate, then that means that the graph is concave. And concave graphs are when f double dashed is greater than 0. That's the rule for concave. You learn that in A-level maths. Now, when you look at this, this is wrong, this is wrong, I mean the sign's wrong. So it's going to be one of these last three, right? Because they're the only ones who talk about f double dash greater than 0. Now, when we look at the other condition that it's talking about, f dashed of x less than 0, so it's got a negative gradient. Well, here I've got a positive gradient, and I've got this overestimate here. So that could be true, I guess, but it's not the one I've got. And now the problem with E and F is that it's claiming that you must have a negative gradient, right? Only if the gradient is negative and the second derivative is positive. But it can't be only if, because here's an example of a positive gradient and a concave overestimate, right? So the answer has got to be D, because it's the only one that doesn't say that I can't do this. In fact, what D is talking about is this graph here, where the gradient is negative, but you still get this concave kind of idea going on and the overestimate with the trapezium. But because it's only saying if, that's fine, because it doesn't discount this also acceptable version of doing it here, whereas these only ifs do. So the answer is only D here. Good. Question 13. So another necessarily true one. Now, this is a good instructive moment here, because I'm actually not going to use counterexamples for this, because coming up with counterexamples for a question like this is quite difficult, I think. So I'm just going to think about this logically, even though I talked about counterexamples earlier, and I do think they're really powerful. But here I'm going to look at this logically. So what I'm going to do is here there's a question about 1 to 3, x 1 to 3. Now here there's nothing from x's 1 to 3. There's x from 0 to 3 and x from 0 to 1, but not 1 to 3. So that gives me a hint as to what I should do is take this and break it down to somehow be between 1 and 3. And the obvious way to do that is to break this one up between 0 and 1 and 1 and 3. And the reason that occurred to me is because of this hint here, but also because that means that this thing here cancels with this thing here, and I just get this statement. Now, how is this helpful? Well, f of x is the function. When you square a number, it becomes positive, right? So f of x squared is a function that is only above the x-axis, because even if it was f of x was below the x-axis, it squares to be above it because it squares to be a positive. So the integral of f of x, all squared, is definitely a positive thing, because the graph is just above the x-axis only, or it could be 0 as well. So this is greater or equal to 0, this integral here. Which means if we add it to another integral to make 0, that means this integral is less than or equal to 0, because obviously it needs to cancel out. Now, if this integral is less than or equal to 0, that means the function itself must have been below the x-axis for some of that in order to get that negative area. So this is necessarily true, because it's exactly what I've just said. F of x needs to be below the x-axis between these 2 points in order to make this balance out. So that is necessarily true. Next one. Now notice when you look at this, it's very similar to this, except it ignores this. So let's just take this again and do the same kind of analysis. This is a positive integral, as I've said. So if I just ignore it, if I just get rid of it, this left-hand side becomes smaller because I'm removing a positive number from it. So if it becomes smaller, I can put this sign in instead, and that's exactly what it says here. So that's also necessarily true. So both 1 and 2. Answer is D. 14. Arithmetic sequence starts A, common difference D. Has some property here which is quite cool. When you add up the first m terms, it's equal to the sum of when you add up the first 2 m terms. So for example, when you add up the first 3 terms, it equals the sum of the first 6 terms. Here's an example with 4 terms. Add up those 4 equals the when you add up the first 8. And you can see clearly why it's true, because those last 4 terms all just cancel with each other. So you end up with just the first 4 terms. So that's pretty cool. Now, it's asking if you have sequences of this type, which of the statements here are true about them. Okay. Firstly, it's saying, is it sufficient that AD is less than 0? Now, A and D is the first term and the difference. When you multiply 2 numbers to make something less than 0, that means one of them must have been negative, and the other one must have been positive. Now, it's pretty clear that this is necessary, I think, because if you just take a sequence that has a positive starting value and a positive difference, you're clearly not going to get any of this cancelling action that was necessary to get this to work. And again, if you take something that's negative that starts negative and takes away a number, again, no cancelling is going to happen here. So it's very clear that this is necessary, but that's not sufficiency. Is it sufficient? And to work out whether it's sufficient, again, saw it earlier, counterexample. Can you find an AD less than 0? Can you find a sequence where A is maybe positive, D is negative, that just doesn't have this property at any point? And you can very quickly come up with this one here. At no point, so A is positive, D is negative, so they multiply to be less than 0, but at no point does this actually work, right? If you call it about one term, it sums to 2, but then 2 terms sum to 3. If you cut out 2 terms, adds up to 3, but then 4 terms adds up to 2, and so on. This just doesn't work. I don't think, at least. No, it doesn't work, right? If you do the first 3 terms, you get 3, and then the next ones add up to -6, you get -3. No, it doesn't work. Okay, so this doesn't work, so it's not sufficient, right? Because again, here's a counterexample. Here's a thing that does this, but actually doesn't do this. Is it necessary that D is even? Well, I look at this and I go, well, D is -1 here, right? Which is odd. Can I just mess with this to make it work? And then I can obviously disprove this. And yeah, right? Because look at this sequence here. Those 3 cancel with each other really nicely. So if I just start the sequence earlier, like here, the first 3 terms add up to 9. And the first 6 terms also add up to 9, because these 3 cancel. And the difference is only 1, which is not even. So it's not necessary. So neither of them are necessary. Sorry, neither of them are true. This one is necessary but not sufficient. This one is probably not necessary or sufficient. I haven't thought about it. Maybe that's your homework. Anyway, question number 15. Which of the following is necessary and sufficient? More of these words. Excellent. Again, you could think about counterexamples here. It's easier just to analyze this properly, I think. When n is 1, you just literally get the first thing, which is sine pi over 3, which is that. So this clearly works for n equals 1. It works. But that's not necessary and sufficiency. Right? Just because something works doesn't mean that you can say it's necessary and sufficient. Again, go back to that silly example I had earlier. Just because someone watches my videos and gets an A* in Maths A level doesn't make it necessary and sufficient to watch my videos to get an A* in Maths A level. Lots of people have never heard of me and have got A stars. Well done to those people. Doesn't make it necessary or sufficient. Okay, so just because this works doesn't mean it's the answer. If you make n 2, you get sine of pi over 3 plus sine of 2 pi over 3. Now, we have to work out what sine 2 pi over 3 is. We need to draw the sine graph. Sine 2 pi over 3, well, pi over 3 just gets you to here, which is root 3 over 2. 2 pi over 3 just gets you to the same thing, root 3 over 2. Now, sine 3 pi over 3, so when you add up these two, by the way, you don't get this, so it doesn't work for 2. When n is 3, you need to work out what sine 3 pi over 3, which is sine of pi, which is 0, is. So it's just here. When you add up those, you still don't get this. So it doesn't work for n is 3. When you use 4, you get this because you end up down here, which is just going to be the minus root 3 over 2. And actually, when you add up the first 4, this cancels with this doesn't matter, and you just get that. So this does work for n is 4. And that's really helpful to know, because which is necessary and sufficient? Well, if it works for 4, this can't be necessary and sufficient because 4 isn't that. This can't be, this could be, this can't be, this can't be. So the only possible answer here is D, right? Because it works for 4. I didn't need to write this. It works for n is 4, and n is 4. The only thing here is D. Now, logically, you can see, maybe if you look at this graph, why this would be true. You don't need to do this in the actual exam. You haven't got time, maybe. But, like, if you just go one beyond the point where it hits the axis every 3, right? This is the 3rd, this is the 6th, this is the 9th. If you go one beyond that, this cancels with this, and you're just left with that, which is the root 3 over 2. If you go one beyond, these all cancel with each other, and you're just left with this, which is the root 3 over 2. If you go one beyond this, again, this cancels with this. This one will cancel with this one. You're just left with the original one. And you always just end up with root 3 over 2. So it's kind of logical when you think about it that way. But again, you don't need to really do that in the exam. Okay, so another spot the mistake question to do with FTC, fundamental theorem of calculus. So this is it. It's essentially saying when you integrate a value between x and 0 and then differentiate it, you just get the same function you started with, just with x instead of the dummy variable t. A student does this as follows. Now, the first thing I see here is that, well, okay, let's look at each point, each thing as we go along. This is clearly okay, because this is actually what I did earlier in the video, right? This split the integral between 0 and 2x and 0 and x, and then just taken away, so that's clearly fine. This is clearly fine because that is exactly FTC, right? They've got the function here, they just repeated the function just in terms of x instead. That's clearly fine. Now this, I actually thought this was completely fine when I first saw it. It looks like FTC, but just be very careful. It's got a 2x instead of an x here. So it's possible, and it's definitely worth checking, that this is actually okay, because it might not be. You know, you might not be completely versed in FTC. You might have not done it. You might not be a maths professor who thinks about it all the time. Just check it, right? So what I did was I just checked it for the simplest thing I could. Let's just pretend the function is 1. And then we just ask ourselves, does the integral between 0 and 2x of the function f of t, which is just 1, equal that function, but replacing, because there's an x here and there's an x here, replacing that with a 2x, which is what they've done, right? They've just replaced this function t squared with a 2x squared because of this 2x. Are you just allowed to do that? And of course I can do this integral. 1 integrates to x, 1 integrates to t. Substitute in 2x and 0, you clearly get 2x, but when you differentiate 2x, you get 2. And of course f of 2x is just 1 because the function is defined to be 1. And of course 2 doesn't equal 1. So the FTC doesn't actually work like this. You can't just replace this upper bound with whatever you want. And so this is the mistake here. Question 17. I'm pretty sure my year 8s could do this, but I'm not sure. This is very instructive though, right? Because these questions do generally get harder as you go further into the paper, but it's definitely worth looking at all of the questions. Don't just assume that they're going to be really hard at the end. Look at them, because you'll see a question like this, and I also think maybe question 19 is quite easy. You see it, this question everyone can do. Everyone should get the mark on this who's taking TMUA seriously. It's not hard. You just set up 2 lists of 3 numbers. You follow the instructions. This is literally a year 8 question, right? When you put a median of 8 in here, median of 9 here. If the mean is 10, that means they sum to 30, obviously, and sum to 36 here. And then just a little bit of logic is required here. All the numbers have to be different, apparently. What's the smallest possible range? So I want this number to be as big as possible and this number to be as small as possible. If I want this number to be as small as possible, I want this one to be as big as possible, so that I can get the sum to 36 as easily as I can. But the biggest I can have that number, because they need to be in size order, and because there's an 8 there, and because they're all integers and all different, the biggest I can have this number is 7, which means if they sum to 36, then this is 20. And now, okay, well, I just move across here. I want this number to be as big as possible, remember, which means I need this number to be as small as possible. The smallest I can, well, the biggest I can have this is 6, right? Because it's got to be less than 8, but I can't use 7, which makes this a 16. Irrelevantly, mean is 4. The range is 14. That's just it. That's the whole question. 18. So we've got 2 polynomials, cubics. F of x minus g of x is always bigger than 0. Now, what that means, and again, necessarily true. I'm just going to use counterexamples here because you know that I am. All that this means is that f of x on the graph is always above g of x, right? There's always a distance, a positive distance between them. That way when I do this one, take away this one, I always get a positive distance between them for any value. Now, of course, all I've done here is I've shifted g of x up by some number. All I'm saying here is this is the same, and I don't have to do this, there are other ways to do it, but one way to do this, to make this work, is to just make f of x the same polynomial as g of x, but just adding some constant on. Now, of course, if I do that, if this polynomial is the same as this one, just with a bigger number at the end, then a is equal to p, right? So this is clearly not necessarily true. Here's a counterexample, where a is equal to p because it's the same cubic, the other one's just been shifted up a bit. This is a bit more difficult to deal with. Let's look at this first, because this is very simple. D bigger than s. D is the y-intercept of the black one, f, and s is the y-intercept of this. Now, D clearly has to be bigger, because again, I've framed this as the black graph always needs to be above the red. That's true for the y-axis, so D must be bigger than s. So that's clearly necessarily true. Last one, a bit of analysis is required here. You actually just take them away. Group them all up by their x coefficients, and then say, okay, if b is equal to q. Now, if b is equal to q, then this goes away. So we're left with this. Now, the problem here is that this is a cubic. It's a cubic graph, right? And cubics either start down here and up here, or start over here and end down there. But what they're not is they're not always bigger than 0. you will never have a cubic, a proper cubic, that's always bigger than 0. Again, because they start here and here, or start here and here. They're always down here somewhere. So this can't be the case. Actually, what must be the case is A must be equal to P. And this can't actually be a cubic. So if A is equal to P, we get this. But again, you do the same logic here. This is a line. This is mx plus c. But lines either do this or this. And either way, they're always some of it is always below the x-axis. Some of it is always less than 0. So actually, you need c to be equal to r, which is exactly what this is saying. So that's necessarily true as well. We need c to be equal to r, and we just need this to be a constant, which is up here somewhere, where d is bigger than s, which is exactly what this one was saying anyway. So yeah, the second two are true there. 19. Again, yeah, I said this, I think, in question 17. This is another question that I think everyone should get. It's not hard. You just try it out a little bit. This is just a game. If you put a truth, I've named truth as tick and lie as cross. Truthers are saying all my neighbors are liars. They're telling the truth. So all of these people must be crosses. Except, sorry, neighbors only count sharing a side, not a corner. So this person could be a truther, but that means these two are liars because he's sharing sides there. Of course, if this is a liar, this is a liar, this is a truther, because he's saying, oh, people next to me are liars, and these are liars, that's good. And this can be a truther, this can be a truther. And I fitted 5 truthers in here. And it sort of feels like that's the most I can put in here. It feels like it'd be hard to put 6 truthers in here. And then you look at the answers and you notice that there's no option to have 6 truthers. So the answer must be 5. So that's good. So that's the largest number of truthers I can get in here. Then you just try something else to try and find the smallest. So what if you put a truther here? Then this must be liar, 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 which is good. I got 3 liars already. You can have a truther here if you want to, but also you don't need to, right? You could put a liar there because liars are saying all my neighbors are liars. So they're allowed to have some lying neighbors, they just can't have all of them. So I just need this person to be telling the truth down here. And then this person is still lying. When this person says all my neighbors are liars, he's lying because this person is telling the truth. And likewise, that's for the same for the rest of it. So I can get 3 truthers in here. I didn't look too hard to see whether I could get 2 or 1 in there. It seemed pretty implausible that I could. And I just sort of left the question there and said that was the answer, which it turned out that it was, so that's good. Question 20. This is, I think, the hardest question that TMUA has ever asked. It's really rough. If I'm being honest, I think this is the kind of question where you just circle an answer and realistically spend your time looking at other questions that you might actually get. But if you've read all of the logic notes on TMUA and you've practiced this a lot, then you should give this question a go. I just think it's so beyond the realm of normal A-level maths that you'd have to go quite a long way out of your way to actually be able to get this kind of question right. But if you have, really well done and good work. What you want to do for this kind of question, statements like this are tricky and not very helpful to work with together. So you want to change everything to an if-then statement. If something, then something else. Now, there are rules that you have to follow to do this. Essentially, if you see only if, then the way that you set up the if one of these two things, then the other, is you set it up this way. So if you see only if, then that means if this, then this, right? That's if you see only if. You set it up this way. If you see, and that's going to be the same for this one and the same for this one. If you see if, that means you set it up the other way, right to left. You set up the if-then statement as if this, then this. And that likewise for this one. And if you see if and only if, you can maybe logically work this out. You set up both statements. You set up if this, then that, and if this, then that. Right? Now, okay, if you just have read all the notes on logic and have maybe practiced a bit, you might just know that. Now, I actually struggle to remember these rules here, so I have a really dumb example that's locked into my head that helps me remember them. I never forget this one. This one's really easy for me to remember, but I always forget which way around these two are. And my dumb example is this: beautiful if Chris Hemsworth. Now, how do we write this statement if this is the thing? Now, if Chris Hemsworth, then beautiful is the statement, right? If this thing here is correct, which it obviously is, then we can write this: if Chris Hemsworth, then beautiful. We can't write if beautiful, then Chris Hemsworth, because notice how this statement here, there's no exclusivity. This statement is saying Chris Hemsworth is beautiful, but it's not discounting other people or things from having beauty. like all the people still watching this YouTube video to the end. So this statement is not true. So if we see if, this is why I have this example in my head. If I see if, then I know I set up this one to this one. I set it up right to left if I see if. And I can do that with this. Beautiful only if concerned with. This actually means this is removing the exclusivity, isn't it? Beautiful only if Chris Hemsworth is saying nothing else is beautiful aside from him. So you can actually make the statement now, if beautiful, then Chris Hemsworth. So you can set it up left to right. So this is the dumb example I have in my head that helps me remember which way around these are. I don't need them for this, and the analogy kind of breaks down here for this one. But it doesn't matter. I just use this to remember these two rules. I remember this one always, and now I've set up these, and this question, we can actually make a start on it, and it should be much better, because setting up if-then statements is just much easier to use than these. So let's go through these. First thing I notice is the statement F here. This bit of F is this bit of B. So if F is true, then this and this is true, obviously. But if this is true, then this is true, and I'm only wanting one of these things to be true. So if F is true, then B is, so therefore F can't be true. Notice how that doesn't work the other way around. If B is true, that doesn't necessarily mean F is, because if B is true, then sure, this is true, but this might not be. So I can't discount B, but I can discount F from that. Let's go from the top then. A. If x is greater than 0, so let's just get out a graph and say, okay, x is greater than 0 is over here, right? The x input is over here. X less than 0 over here. F of x is the y, essentially. So f of x greater than 0 is up here, f of x less than 0 is down here. So when this statement says this, if x is over here, then f of x is down here. So this graph, if it follows this rule, is something like this. If x is greater than or equal to 0, then f of x is less than 0. It doesn't say anything about what happens over here. This could do whatever the hell it wants over here. It's just dictating this part. Then we look at the other statements and we say, well, if any of these are necessarily true looking at this, then A can't be true because it's implying another statement. So we go to B and we go, okay, if f of x is greater than 0, then x is less than 0. You look at this graph and think, well, actually, the only places on this graph where f of x is greater than 0 is when x is less than 0, is over here. So actually, A and B are implying each other. So A and B can't be the answers, because, and if you've read the logic notes really heavily, you might have heard of contrapositives and stuff. Essentially, these are actually contrapositives of each other. I don't really work with them very often because it's not anything that I teach, so I tend to just get out examples. But A and B are talking about the same graph, essentially. So we move on to C. C is saying if x is greater than or equal to 0, so that's again over here, then f of x is greater than 0, so that's up here somewhere. Again, it's not saying anything about this section, it's just saying if x is greater than 0, we're up here, not saying anything over here. Now that's clearly different to what we've looked at before, so it's irrelevant, so we'll keep it, and we'll look at number D. So D, if x is less than 0, so if we're over here, f of x is less than 0, so we're down here. Again, it's not saying anything about what's going on over here, it's just saying if you're over here, then you're down here. Okay, so these two graphs are completely different, it looks like, so no implications there. Let's look at E. If f of x is greater than 0, x greater than 0, we have the same thing. Look at this graph. The only times f of x are greater than 0, x is greater than 0. So this is actually the same graph I would draw if I was looking at E. So again, D and E are the same statement, and again, they're also contrapositives of each other if you know what that is. I might make a video on that on its own. But anyway, the only one that doesn't imply any of the others is C. That is a really, really rough question, but really well if you get it. Thank you so much for watching, and I'll see you next time.